Hello, we have learned about the joint distribution of two random variables x and y. So let's say we have either the CDF of these two random variables, and now we consider one function of these two random variables. So we have a function with two inputs, g of x and y, and then we have z as a function of g of x and y. So this distribution is given, we know that, and we want to find a distribution of the function of these two random variables. So the outline of this section is that these two random variables, and then we have z, and we have two inputs, x and y, and we want to find this distribution of that. And we will have several examples. This is perhaps one of the most difficult part of this course. In here we'll reintroduce the circular symmetry concept, and we will see that if the inputs have circular symmetry, how we can simplify some of the problems. We will, as example, we'll consider also the minimum, maximum, and sorting operations, and so on. So we know how to describe the joint probabilistic behavior of multiple random variables. One of them is the joint CDF, which is fxy of x and y, which is probability that this is smaller than this one and y is smaller than y, or using the joint PDF, which is the derivative of that, fx of x and y, or the characteristic function of the x, y of, let's say, omega 1 and omega 2, which is basically equal to mean of e to the power of j omega 1x plus j omega 2y. So this is also another form of a distribution. Or if you have a series of all moments of this, if you have mean of x to the power of n and y to the power of m, so let's say if I denote this by m of a moment, if you have this function for all m and n, so let's say mu of n and n, so if you know that, then you also have the distribution, because this could be Taylor series expansion of the moment generating function. So the problem is that if the distribution of x and y is given in one form or another, we want to, and then we have another given function g, and let's say z equal to g of x and y, we want to know how to find the distribution of the output. At the first step, we will find a systematic way in order to describe the joint PDF of this one in terms of the joint PDF of the input. So the first part of this course is the finding the CDF of a function of two random variables, or finding the PDF of a function of two random variables. So assume that any function is given, and then we form this new random variable. We want to find the distribution of z in terms of the joint distribution of x and y. So the first thing to do is to, if you want to have the CDF of z, z of z is basically is equal to probability that z is smaller than or equal to z. So probability of this event. So what is the meaning of this event? Means that on the line of, let's say this is my line z, so what is the probability that z falls somewhere here? And remember that we have an x, y plane, and in this point x and y is mapped through this function which has two input, and you have function g, and then this is equal to is mapped to somewhere here. So we want to know what are the set of points on xy plane. So this dz is the set of points in XY plane or in R2, which is this 2D plane, which are mapped into this interval from minus infinity and point Z. So we want to, if you want to measure probability of this event, we have to measure probability of this set which are mapped onto this interval. So dz is this set point. So this probability fz of z is equal to probability that random pair x and y as a function of c, they fall into the z. Okay, so once you determine this set dz, you could say that this is double integral of the joint PDF of x and y dx dy over this dz. So you know that probability of any event described by x and y is equal to integral over that area and so on. So this is what we have. So let us see how we could use this method. So basically this z is equal to this one and this is equal to this event, and this is basically equal to say that x and y falls into the z. Okay, and this is what we have to calculate. Okay, so this is a double integral that we denoted by abbreviation as a single integral. So remember that. Let us, if you want to consider dz, so let's say this is dz. dz is the set of point those x and y such that g of x and y is smaller than or equal to z. So inside this set, this inequality is satisfied. So if I consider d of, if I increase z, if I increase this one, this set increases. So if I consider this one, g of x and y being smaller than or equal dz plus dz, okay, so more points will satisfy this inequality because this will be relaxed. So this area will become d of z plus dz. So the difference between the two is going to be outside dz. So this is outside the z, but inside dz plus dz. Basically, this is the difference of the two sets and is also equal to d z plus dz intersection with the z bar complement of that. So that means that outside of these but inside of these, which is intersection of the two. So this is intersection of complement of that with the other. So what we do, this is what we define. Basically, because you want to be outside of these, bigger than z and smaller. So these is a new event. So if I calculate probability of that, probability of z being bigger than z and smaller than z plus dz is equal to probability that x and y is inside this delta z, delta dz, which is equal to integral over delta dz. So remember that we have two sets. This is dz and this is delta dz. So you calculate the integral over the difference of fx y of x and y dx dy. Now what I do is that I consider this dz to be as small as needed. So we make it as small as what we need in order to do what? In order to make this function over this area to be, if this guy is very small, the PDF of Z, because what I have here is that this is Z plus dz, and this is the PDF of Z, fz of Z, which I don't know. So if dz is very small, such that this function is almost constant, such that this line, which is not flat, is almost constant, then I could say that this could be approximated by fz of Z times dz. So you could say that this area is equal to this length times this height. Okay. And also I want to calculate this integral. So this way I could calculate directly the PDF of f of z. If I divide both sides by dz, then I can get an expression by the PDF. So I could directly calculate the PDF of my random variable. So I do this approximation so this is equal for dz be small enough, then dz tends to 0. And then we have to find some tricks to simplify this double integral.